In Unit 3, this is Lesson 4, and we're going to talk about related rates. And I feel like in speaking with Mr. Brown from last year, related rates is definitely a topic that you did get to spend a decent amount of time on. So I'm hoping that as I start going through this, that a lot of that from last year will start to come back a little bit. And let's take a look at the lesson. So it says you've seen how the chain rule can be used to find dy dx implicitly. So that means that when you're taking the derivative of a y with respect to x, you have to multiply in that extra dy dx. That's that chain rule at work, assuming that y is a function of x. Then we're going to use that same concept to take the derivative of two or more variables that are changing with respect to time. This is really the more real life application of a derivative because you have things changing and sort of the independent variable is time. That as time passes, the size of something is going to change or something's going to melt or grow, and it's time that's passing as our independent variable. So if we take the derivative with respect to time, then what happens is any variable that is not t, you need to apply the chain rule to and multiply by the derivative with respect to time of that variable. The first two examples are not giving us numbers to plug in. We're just practicing getting this derivative with respect to time. So let's take a look at number 1. It says find the following related rates equations. The water is drained out of a conical tank. The volume V, radius R, and height h of the water level are all functions of time related by the equation, and it gives us the volume formula for the cone, the conical tank. Write a related rates equation that relates dV dt to dr dt and dH dt. Any d dt of a variable is that rate of change of the variable. So before we even take the derivative, I just want to make sure that we understand what each variable means. dV dt is the rate, the volume changes with respect to time. And then when you change it to a dr dt, the dr dt is the rate variable. So it's the rate, the radius changes with respect to time. And so on. dH dt would be the rate that the height is changing with respect to time. I'm not going to write that one out because now we get the idea. The related rates variables are the rates of change. So we're going to take the derivative with respect to time, d dt, of both sides of our volume formula. So when we take the derivative of v, just like if I was going to take the derivative of x is 1. But since it's a v with respect to time, it's 1 dv dt, or I'm just going to write that as dv dt. Now when I take the derivative with respect to time, I feel like some of you get a little tripped up as to what to do with the constants. A constant multiple multiplies to the derivative of the function. So I'm going to bring that pi over 3 to the front because it stays there. But then I want to do a product rule on r squared h. So this is going to be my u v. So my product rule is u v prime. Now the derivative of h is 1 dH dt. So I'm just going to put a dH dt in there. Plus v u prime. Well, the derivative of r squared, I have to start chain rule with the outside function. So first the power rule, 2r, and then the derivative of r with respect to time, dr dt. And this really was just asking for dv dt with respect to the others. So this is good enough. I don't have to distribute. I wasn't given any numerical information to plug in. This was just having me practice getting the related rates equation, which is the derivative with respect to time. Questions? All right, let's take a look at the question. Oh, sorry. Sometimes they might ask you to manipulate the related rates equation. So here's another one. Volume V, radius R, and height H of a right circular cylinder are related by this equation. Volume equals pi r squared H. Part A is asking, how is dV dt, so the rate of change of the volume, related to dH dt, the rate of change of the height, if R is constant? So if the radius is constant, a good way to think of this is, let's say we had, we're talking about a cylinder. So let's say we had a can of some sort that we were filling up with water. So the radius of the water as this fills up, that's going to stay the same, but the height is going to change. But as I fill this up, if I'm thinking about the rate of change of the water, the radius stays constant, even though it is changing because we're filling it up. So how would you have a related rates equation that way? Well, remember I just went over with that pi over 3 that if it's a constant, it just stays as a constant multiple. So for part A, if we're taking the derivative with respect to time of both sides of our equation, the big difference here is that R is going to be treated as a constant. It's not changing. So both the pi and the r squared are constant. If something is constant, it means there is no rate of change with respect to time. So when I take the derivative, dv dt, the pi r squared is a constant multiple. And then I just have to multiply it to the derivative of the height. The derivative of the height is 1, which I don't have to write, dh dt. I don't need to utilize an entire product rule when you have a constant multiple. Really, if you did, if you felt like, oh, I think I should have done a product rule, the second half of the product rule always cancels out because the derivative of the constant is 0. So constant multiple rule is just like the reminder of if one of them's a constant, the second half of the product rule always goes to 0. In part B, they just flip-flop for us which one's constant. We want how is dv dt related to dr dt if the height is constant. So now if I'm going to take the derivative with respect to time of both sides, it's a little out of order in the terms that the constants usually are grouped together in the front, but now it's the pi and the h that are constant. So dv dt, let's pull the pi and the h to the front. Now we're taking the derivative of r. So r squared, we first start off with the power rule, 2r, and then dr dt. And again, since we don't have any values to plug in, we're just getting what we call our related rates equation. So if the height of something of a cylinder is staying constant, maybe it's something that's like blowing up or expanding, that the radius is getting bigger, but the height is staying constant. Questions? At the bottom of the page, I figured it would be helpful if we just write some steps out that we'll be following in order to answer the next questions, where we're not just being asked to do a related rates equation. So when you're given a related rates problem, it's very important that if you're not given a picture, that you sketch some sort of picture so that you can identify the variables and the constants. Draw a picture and identify the variables and the constants. This is so important for what we just did. The variables versus the constants will depend upon how we treat it. It might have a letter R in the equation, but if in the situation the radius is constant, you need to know how to treat it. Is it a constant or is it changing? So it's a variable, because it's going to kind of depend upon how the situation plays out, if it's changing or if it's constant. 2, identify the given numerical information. Identify the given numerical information. Do I know volume? Do I know the rate of change of volume? Am I given a radius? So identify what you have in terms of what does it represent. Three is identify what you are solving for and any unknown values. What are we solving for? So what's the ultimate question? Identify what you are solving for. But also any unknown values. Sometimes there's something that you kind of just don't know anything about, and that might take you on a little detour that you have to figure that out first before you can actually answer the question. So what am I looking for ultimately? And is there anything that's kind of unknown that might be holding me back? Decide on the equation that relates the variables. Could be a geometry formula, like our first 2 examples, a volume formula, an area formula, something like that. Maybe it's something like Pythagorean theorem, or that, trying to think of another good example, a trig equation. Something that has to relate all the pieces in the problem together. What equation ties everything together? Decide on the equation that relates the variable. Once you do that, you take its derivative with respect to time. That's what we just practiced, the related rates equation. Then you're going to plug everything in and solve. Looks like we're good on time here at home. Are you guys done with the steps? All right, so let's do an example. Air is being pumped into a spherical balloon at the rate of 4.5 inches cubed per minute. Find the rate of change of the radius when the radius is 2 inches, given the volume formula of a sphere is 4/3 pi r cubed. All right, so if we have a spherical balloon that's being pumped up, the first thing that you want to get a visual of in your head is, if our volume formula is based on the radius, if we're blowing this up, is the radius or the volume remaining constant when we blow it up? No, no constants in this one. Everything's expanding. All right, so let's see what we're given. Air is being pumped into, this is going to be important for our sign. Air is being pumped into, so it's increasing, a spherical balloon at the rate of. That is my phrase that's letting me know I'm getting a DDT variable. It's the rate of, so it's the variable of 4.5. Now, units are very helpful in deciding which rate it is. The air is being pumped in at 4.5 inches cubed per minute. Is that the rate of change of volume or the actual radius? Volume. And the inches cubed is the dead giveaway there. The air being pumped in, so the overall air is the volume, but for sure that 4.5 inches cubed is the giveaway. So they're giving me dV dt. Now, rates of change, derivatives have a sign indicating their direction. So since it's being pumped into, this is going to be a 4.5, positive 4.5 inches cubed per minute. I'm going to leave the units off of my list for right now. Find the rate of change of the radius. So since I'm being asked for a rate of change, I know I'm looking for a related rate variable, or a DDT, and it's the rate of change of the radius. So dRdt is what I'm looking for. When the radius is 2 inches, so what is going to happen is you're going to be given sort of a snapshot, or a split second, that then you're analyzing the rates of change, because the rates are related. They can be different at different points in time. Now remember, the underlying independent variable is time. As we blow this up, as time passes, it's expanding. Since our volume formula is not in terms of time, it's based upon the radius, what we have to get is a snapshot as to, well, when are you asking about this rate? So the radius itself, remember, isn't a constant. It's just that we want to know how fast it's increasing at the split second when the radius is 2. Another way that they could give this to us is at a certain time, but then they would have to connect how the volume was changing according to time. So it's easier for them to give us a split second that the radius is, in order for us to to evaluate this. I do not want to plug in the 2 into the volume formula. I'm not being asked to calculate the volume when the radius is 2. I want the rate that the rate that the radius is changing when the radius is 2, meaning I have to take the derivative with respect to time first. I need the related rates equation before I plug in anything. 4/3 pi is a constant. Then I've got the derivative of r cubed dr dt. Cancel those 3's, make things a little easier for us. And now we can plug in what we know. We know that dv dt is 4.5. 4 pi, the radius. Here's now where I'm saying, well, what about when the radius is 2? So now I can plug into, let's make a little note. Wait until after you get the related rates equation to plug in r equals 2. And that really goes back to our first thought of, is anything constant? The only thing you can plug in the beginning is if it's constant, because it doesn't have a rate of change. If anything that's changing, you got to get the related rates equation first. So now we just have to simplify this. So we've got 4, 2 squared is 4, so 4 times 4 is 16 pi, and we're solving for dr dt. Now, this is just a good opportunity to talk about silly mistakes in the calculator. If we want to get the decimal approximation, depending, if this was non-calculator, this would be our answer. And since it's just radius, it would be inches per minute, not inches cubed, right? Radius is just in linear units. But if I wanted to plug this into the calculator, silly calculator error is to forget to put parentheses around the denominator. So we're doing 4.5. I have to do divided by parentheses 16 pi in order for the right order of operations to happen. If you do it without parentheses, PEMDAS actually tells the calculator to do, sorry, let me get the right way in there again. And then the wrong way would tell the calculator first divide by 16, then multiply that final answer by pi. Notice you get a totally different decimal answer because you need to tell the calculator 16 pi is in the denominator and you need parentheses in order to accomplish that. So if we were going to do this calculator active, it would be 0.0895 inches per minute. Questions? Let's try another one. An airplane is flying on a path that will take it directly over a radar tracking station. If the distance between the plane and the tracking station, S, is decreasing at a rate of 400 miles per hour when S is 10 miles, and the plane is flying at an altitude of 6 miles high, what is the speed of the plane? Related rates questions, you have to read, I would say, a minimum of 4 times when you're doing this, because you got to first read it, get an idea, and then you got to go through and dissect it and draw a picture. So we have an airplane is flying on a path that will take it directly over a radar tracking station. All right, so here I'm going to draw the ground, and I'm going to put my radar tracking station here on the ground, and my airplane is in the sky.
Yours doesn't say 6 miles high, like in the beginning of the second, a little different.
Oh, I have 6 miles high here. Where's yours?
Ours is at the beginning.
At the beginning too? Okay, but it's not a different number, just somehow I edited the question and used an old version of it?
Yeah.
Okay. On yours it says it twice?
Yeah.
Okay. I feel like maybe I noticed that it was twice and changed it on the PowerPoint and not on your handout or something like that. All right, as long as we're not dealing with different numbers then, but I'll make a note to fix that. Now, it's not saying that the airplane is taking off or landing. It's saying the airplane is flying on a path that will take it directly over the radar tracking station. So this little dot was my radar tracking station. Okay, if the distance between the plane and the tracking station S, all right, so I need to connect the plane to the tracking station, and they're telling me use the variable S for that, is decreasing at a rate of 400 miles per hour. Well, I'm going to start building what I know then. If the rate, that's the ds dt, is decreasing, it would have to be negative 400, and we're in miles per hour. I'll bring back units later. All right, if the distance between the plane and the tracking station S is decreasing at a rate of 400 miles per hour, when S is 10. Now, let's think about S for a second. As the plane continues to fly, is S staying constant or is it changing? Changing. So S is changing. So I don't want to plug in S until I get a related rates equation. That S is part of my snapshot when I'm trying to look at and analyze. Okay, when S is 10 miles and the plane is flying at an altitude of 6 miles high. So an altitude, that's a height. Now, if the plane is flying directly over the tracking station, is the altitude changing or is it constant? This time it's constant. Now, altitude in certain situations, if they were talking about a takeoff or a landing, then maybe it's changing. But right now, 6 is a constant. So I don't need to come up with a variable for that. I can just leave that as a 6. What is the speed of the plane? All right, well, the speed is how fast it's going forward, right? So first thing I would need then is a variable for this direction. So let's call it X. because it's going horizontal. Now, when I'm thinking of the plane, I am kind of thinking of it up here, but really, I just made a big old right triangle. So let's use the horizontal variable down here instead, because what equation now relates x, s, and 6 together? Pythagorean theorem. So it doesn't matter that we're saying x down here, it's the same corresponding distance as up here, and we can set up that x squared plus 6 squared is equal to s squared. And notice only the constant can be plugged in to start. Only the constant can be plugged in to start. The S information has to hold off until I get the related rates equation. Now, 6 squared, that's just 36. Sometimes it might make it easier for you if you square it so that you don't try to do a power rule or something silly on it because you see the exponent. And now we're going to take the related rates equation. So 2x dx dt. The constant goes to 0, which is why it's so important that we decide what's constant before we take the derivative. Then we've got 2s ds dt. All right, we're doing pretty good, and then all of a sudden we hit a little uh-oh, because we're looking for the speed of the plane. So the speed is going to be our rate of change. dx dt is really the question. What is the speed or the rate of change? The uh-oh that we're hitting is that in my related rates equation, I do have an x, a plain old x, that they didn't give me. But they did start me with the snapshot that s is 10. So if we were to take a picture and freeze frame this when s is 10 and this height is 6, there has to be a corresponding freeze frame for x that fits in the Pythagorean theorem when we take that picture. Does anyone know what it is without actually solving for it? How'd you get it without writing all the work out?
3, 4, 5.
It's a 3, 4, 5 right triangle, but just doubled. So we got a 6, 10. So this has to be 4 times 2, which is 8. So look for things like that, because I feel like a lot of times they utilize those skills to save you some work. But bottom line is, if you didn't think of that, you would have just set up that x squared plus 6 squared equals 10 squared and taken the 2 minutes to just solve. That even though x is a variable, when we take the snapshot when s is 10, the x also has to be an 8. And that's like a little side calculation that a lot of these related rates problem require. So it's important to know, what am I ultimately looking for? And then what am I actually going to need to get there? You might have a few little side roads to take. All right, so solving for dx dt, we got 16 dx dt equals, this is going to be a negative 8, 3 zeros, so negative 8,000. Divided both sides by 16. Well, if I wasn't allowed to use a calculator, I'd cover up these zeros and say 16 goes into 80 5 times, and then I got 2 zeros, so negative 500. Because sometimes you're not allowed to use a calculator.
Wait, does the 36 go away?
Right, because what I did up here, and you're kind of pointing out my laziness, Sanjita, I didn't do this. That I didn't write down that what I was going to do is take the derivative with respect to time of both sides. So this disappeared because the derivative of the constant was 0.
I have a question.
Now the answer is not negative 500. Why? Well, miles per hour, I'm going to need that. But why is it not negative 500?
The speed.
They asked for what is the speed of the plane. The negative is letting us know that the distance is decreasing because it's getting closer to the radar tracking station. So the distance between the two is decreasing. But the speed of the plane is absolute value. So our answer would be 500 miles per hour because the speed is the absolute value of the velocity or the rate.
Someone made a comment on the meet.
Oh, sorry, guys. I didn't see the, no. I'm not sure if you can hear me. No, I couldn't hear you. Hold on, maybe Hi, Jenna. Sorry,
Hi.
sweetie, I didn't have the volume on.
No, it's okay. I just have a question.
Yes.
So in the question above, like for the constants, like you left them as their numerical value, but like why in this one we don't? Like like for the one above, we left the we left the 4/3 pi, and then in this one the 36 goes to 0.
Ooh, great question. Super great question. So in this one, 4/3 pi is being multiplied to the variable. A constant multiple stays there because really it's the beginning part of the product rule that's staying around and the second half is what's going to 0. Multiplier. In this one, our constant was added as its own term. And so the derivative of the constant all by itself is 0. Only constant multiples stay.
Okay, thank you.
Mm-hmm. Other questions? All right. I am going to, because I know we're not going to get to all of these in our last minute. I'm going to have us skip over 5 and 6, skip over 5 and jump to this last question because this is one that the College Board put out, and I feel like I really like how they kind of have us break down this question here. It says, inside a funnel of height 10 inches has circular cross sections as shown in the figure above. At height h, the radius of the funnel is given by, so they're giving us a function for the radius dependent upon the height. Because you'll notice that if I draw like different cross sections as I go, this radius is changing. It's getting smaller, but not even linear. This is not a cone. A funnel actually has a curve to it as well. So the radius is changing as a function of the height. Between 0 and 10, 0 down here, 10 is the height of the whole thing. So let's actually put that in there. They told us that the height was 10 of the whole funnel itself. The units R and H are in inches, and we're just looking at this part C here to kind of get the related rates in here. It says the funnel contains liquid that is draining from the bottom. At the instant when the height of the liquid is 3 inches and the radius of the surface of the liquid is decreasing at a rate of 1/5 inch per second, at this instant, what is the rate of change of the height of the liquid? All right, we read through it first, and now we've got to dissect it. The funnel itself doesn't change. However, this question is talking about liquid inside of it that's draining out. And as time passes, the radius and the height of the liquid are going to be changing depending upon that formula. So the radius and the height of the liquid are variables. They are not constant. So at the instant when the height of the liquid is 3, so that's height equals 3, but not constant throughout the whole problem, just a snapshot. The radius of the surface of the liquid, is decreasing at a rate of 1/5. So if it's decreasing, it's negative. And if they're giving me the rate, they're not giving me R, they're giving me dr dt, the rate of change of the radius. at this instant, what is the rate of change of the height? They want the rate of change, so the dH dt of the height with respect to time. All right, so they gave us this equation. This we wouldn't have known on our own. And we're going to take the derivative with respect to time of both sides. So dr dt, that 1/20th is a constant multiple. It will stay there, multiple. Then the derivative of the 3 on the inside, since it's added, goes to 0. Then we've got 2h, and that h is changing with respect to time, so dh dt. We were given dr dt is -1/5. We were given our snapshot when 3 was the height. And so now we're just solving. So I've got -1/5 equals 6/20 dH dt. To get rid of a fraction, you can multiply by its reciprocal. So if I multiply both sides here by 20/6, this cancels. 5 goes into 24 times. So I have -4/6 or -2/3 dH dt.
Please stand for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Just going to sneak in here that we were in inches
Attention all
per
tenth grade
second.
students who had Miss Van Dorn last year.
And that's it.
If you would